In the last video, we have seen the importance of program block and how to create an interface and also how to create mod boards. That means using mod boards, you are going to specify the directions for the signals present in the interface, okay, and how to use them in the program. That's what we have seen in the last class. Okay, so we know that one in the previous classes we have discussed about importance of interface. Interface is nothing but simply a bunch of wires, okay, and how you are going to use them with respect to DU2, with respect to test bench. So, and for bunch of wires you can also add the signal directions. That's what done with help of mod boards. And next you can add the timing also. Okay, you can add functionality also. So today we are going to discuss about how to add timing for an interface signals. Okay, timing is mainly used in case of synchronous signals. So whenever you are going to drive or we are going to sample the interface synchronous signals in an interface, okay, when to sample, when to drive, okay, what causes the system to work properly. If it is not working properly, there will be some race condition exist. Okay, how it is going to be existing. Okay, with example we will see all these things. So already have taken the arbiter example. In the arbiter example we have a test bench as well as we have a DUT, and you are sending a request. Request and grant are going to be signals which are synchronous to the clock. So whenever you are saying sending request, that means you are driving the inputs to the DUT. So outputs of test bench are nothing but driving signals for the DUT. So whenever you want to drive, okay, DUT, then after saying the request, what you expect is the DUT has to grant. If a request is coming from device 0, then you expect a grant from the DUT for device 0. Okay, so this is if you are applying same clock for both. Okay, they are synchronous signals, so you are applying with respect to clock. When you are applying with respect to clock, okay, so if you are exactly applying at the same time, this is also 100 nanoseconds, this is also 100 nanoseconds, whether you are going to sample the old value or new value, that means this R0 may be updated exactly at this clock edge. So just before this one it has old value, just after this 100 nanoseconds it has a new value. So 100 minus, if you think this is just before value, 100 plus you can think it as just after value. So just before it has old value, just after the clock edge it has new value, even at the same clock edge also. Okay, so here also if it is exactly taking 100 nanoseconds, it may be slightly just before or slightly just after. Depending on that one, it may sample. This DUT may take old value or new value. There will be some ambiguity while driving as well as while receiving the signals. That means sampling the signals. So you must drive as well as you must receive synchronous signals at a proper time with respect to the clock. So if you are driving too late or sampling too early, okay, the test bench may skip one cycle. There will be no operations will be taken done during one cycle if the driving is too late or if sampling is too early. So you can think driving means giving inputs to the DUT. That means outputs of test bench are driving towards DUT inputs. So this situation is called as driving. Whereas sampling is nothing but opposite situation. So sampling, it is test bench is going to be sampling the output of DUT. So That means a grand signal is going to be coming from this one that you are going to sample, and based on that value you have written the code. So this part is going to be called as sampling. Sampling the outputs of DUT. That means they are inputs for the test bench. Driving signals to the DUT, which are outputs of test bench. So output signals of test bench are driven into DUT, whereas outputs of DUT are sampled by the test bench as inputs. So the main problem is there will be some race condition exists depending on which sampled first. For example, think it is this is DUT and it is test bench. So for example, this is also 100 nanoseconds, this is also 100 nanoseconds. So over here the sampling is done at this place, whereas driving is at this place. That means make it as 95 and this is 97. So if you are driving a new value, because at 95 itself sampling is done. So the output of test benches are going to be changed based on the sampling value at 95 nanoseconds. So the updated value of input is applied to DUT. If instead of it you are sampling at 97 and you are driving your DUT inputs are sampled at 95, then the old values are going to be given as DUT. So this timing is very, very important when the test bench has to sample the inputs, when DUT has to sample the inputs. DUT has to sample the inputs means when the test bench has to drive the signals to the DUT. So we are always talking with respect to test bench. So when to drive the signals, when to sample the signals. So these two are very, very important with respect to synchronization of clock. For this, SystemVerilog has introduced a concept which is called as clocking block. The remedy for this one is clocking block. Clocking block is mainly used to specify synchronization of clock and synchronous signals. With respect to clock, synchronous signals, how they are going to be sampled and how they are going to be driven. So clocking blocks used to specify the timing of synchronous signals related to the clock. And these clocking blocks are mainly used by the test benches. So that you can create a proper synchronous model to test the DUT. Next, whenever you are using clocking block, you can ensure that when your test bench is going to be interacting with synchronous signals at proper time. And these synthesis tools doesn't support the clocking blocks, so the RTL code. So that means while writing the design code, you cannot use the clocking blocks. Clocking blocks are only supported by the test bench. They are not supported by the synthesis tools. So we don't use clocking blocks while writing the design. Next, some more important points related to clocking blocks. So if you are going with an interface, how many clocking blocks it may contain? Depending on the design, if your design using 3 different clocks, it can have 3 different clocking blocks. So there will be no limitation of having how many number of clocking blocks in an interface. So the number of clock blocks in an interface is equal to number of clocks you are used in the DUT. So if you are having only one clock, it will be only a single clock expression. So every clocking block should have only single expression. That means single clock. If you are having 3 clocks, so clock 1 will have one clocking block, clock 2 will have one clocking block, clock 3 also. and in the clocking block you are going to specify whether you are going to use pause edge as for synchronous or neg edge for the synchronous, or both edges you are going to use it for the synchronous. Okay, so that is with the help of @pause edge or @clock. @clock means whenever there is an event occurred on clock. So event means change in the signal. Event means change in the value. So it may be 0 to 1 as well as 1 to 0. It may be from 0 to 1 or 1 to 0. That means this is called as double data rate. Your data is sampled at two edges. On both edges the data is going to be sampled, so it is called as double data rate. Okay. And whenever you are using clocking block, you no need to write. Okay, you no need to write in the test bench upon arriving of pause edge clock. So already you have used a clocking block, you are only mentioning the clocking block in the test bench. You always mention clocking block, you never mention the internal signal of the clocking block. And where the clocking block is going to be, the clocking block itself is going to be specified with respect to clock. So always while writing the program block, that means test bench, you will specify only arbiter.cb. That means cb means clocking block. You can think. We will see how to write the example. Okay. So always we refer clocking block only, not the actual clock, while writing the code in test bench, that is program block. So the advantage what you will get is, okay, if you want to change the clock edge, okay, then simply you will change it in the clocking block and everywhere it automatically changes. That's the advantage you may get. Okay. So this is very important. The characteristics of clocking block. Characteristic of clocking block, that means default behavior of clocking block. Clocking block will have input signals as well as output signals. Okay, so clocking block is only used in the test bench. So if you are going with any clocking block where the input signals, okay, input signals of clocking block, for example, they are simply outputs of DUT. Okay, input signals of clocking block are nothing but output signals of DUT, or they are simply inputs of test bench. And output signals of clocking block, output signals of clocking block are simply inputs for the DUT and they are outputs of test bench. So clocking block and test bench are going to be same. So the default behavior of clocking block, okay, when it samples the input signals, when it drives the output signals. Okay, so for example, this is the clock we are going with, and this is the current edge, current positive edge which we are interested in. So at what time this is the next positive edge. So within one clock cycle, okay, when the input signals are sampled, when the outputs are going to be driven into the design by the clocking block. So the default behavior is the outputs are driven back into the design during current time slot. So during the current time slot itself, okay, the outputs should be driven into the design. Outputs of clocking block, that means outputs of test bench, should be driven into the design, okay, during the current timing slot, and whenever they are going to be given to, so you can think test bench, the outputs of test bench are going to be given to DUT and some operations are going to be performed during this DUT. Okay, and after some time the outputs are going to be stabilized. Outputs of DUTs are stabilized after some time of application of input. Then you must sample them. If you are sampling before stabilizing the output of DUT, you will get wrong inputs for the test bench. You cannot get the proper value. Okay, if you are directly sampling the outputs of DUT at this current edge, okay, so you must give sufficient amount of time for the DUT outputs to stabilize during the current cycle. So as late as you may be taking over here at this point. So how can you say at this point? You know that one, there will be some setup time. Setup time for this clock edge is this much. For example, setup time is the time over which the data should be stable before the clock edge. So this is the point the data is going to be get stable, we assumed. So just before that one, just before the data, when the data is going to be stabilized, you are going with this is the minimum requirement, but the data may be stabilized before this one itself. So whenever the data stabilizes, you must sample it, but you should not enter into the next clock edge. So within the current cycle, you are going to sample the outputs of DUT as late as possible in the current cycle. Whereas the inputs driven into the design, that means outputs of test bench, are driving into inputs of DUT, that is at the clock edge itself. So the default behavior is that input signals are sampled just before the design executes. Okay, that means at this point itself, and the outputs are driven back into the design during the current time slot. Current time slot means as late as just before the setup time of next clock edge. Okay, so in other words, the same can be specified in other words like this. The default timing of common clock is to sample inputs with a skew of one step. Sample inputs with a skew of one step. That means, as you have seen, you must take these outputs after some amount of time. That amount of time is going to be specified with #1. Whereas inputs for the DUT, that means outputs of test bench are driving the DUT. They are with delay of 0. Delay of 0 is nothing but at the clock edge itself. So you must drive the signals into DUT with no delay, whereas you must take the samples of DUT, that means outputs of DUT, with a skew of one step. What is meant by this one step, that we will see. Okay, so that one step delay, that signals are sampled in the postpone region. What is meant by this postpone region and other things we will discuss after 2 slides. Okay, you will get clarity. Next, this is the example how to declare a clocking block, how to use the clocking block in the test bench. Okay, so if you are observing, already you have seen an example of interface with mod ports. So this is the interface declaration and mod port declaration for test, mod port declaration for DUT. Everything is same except this part. So a clocking block is defined with the help of clocking keyword. Clocking keyword followed by clocking name. Clocking name can be anything. Okay, it may be CB, CB1 or your name or anything else. So a clocking keyword followed by clocking block and the edge over which it has to be synchronized. So at pause edge clock. So this is declaration of clocking block, and in this one the signals of test bench has to be specified. Signals of test bench that are synchronous signals only you should specify. So output request, input grant. Output request, input grant, and you have not specified reset in this clocking block. That means reset you are going to use. Reset is also output of test bench. Reset is also output of test bench, but it is asynchronous signal. So you are not specified within this clocking block. So only synchronous signals are grant and request. Request is output signal for the test bench. Grant is input signal for the test bench. So you are specifying the directions, okay, along with over which edge it must be synchronous. This is declaration of clocking block. And whenever you are using now clocking in the test bench program, you must use this clocking block name instead of original clock. Okay, how you are going to use it? Like this. Look at this one. @arbitif.cb. Arbitif is the interface name. Okay, Arbitif is the interface name. You see, this is okay. So for this test bench, the input is going to be a arbitrary, which is type of an interface, and in that interface you are going to use a mod port named test. So, and you are going to write the program on the event which occurred on the clock. So you are referring the clocking block now. @arbitif.cb. The meaning of this one is whenever there is an event occurred in the clocking block of interface arbit if. Whenever there is an event occurred in the clocking block of arbit if interface. So if an event occurred means it comes back to this point and where it is referred with respect to clock edge. So whenever a clock edge, a positive clock edge occurred, okay, then you are going to send request from the device 0. This 1 indicates request from device 0, this 0 indicates there is no request from the device 1. And after sending the request, you are checking whether the grant has given by the DUT or not. Okay. For that purpose, you waited for one more clock event. That means one more positive edge. So you waited for one clock cycle. You are checking whether the grant has come or not. That you are going to be displaying. And after one cycle, it may take one or more clock cycles. So you are going with one more clock cycle. You are waiting for one more clock cycle, and again you are going to display whether the grant has happened given or not. Okay, finish. So this is how to declare the clocking block and how to use this in the test bench module. That means program code, program block. So have you observed? Whenever you are using the signals in the clock domain, you must always specify interface name dot clocking block name dot actual signal name. If you are using mod ports, you will not use this mod port as after dot. Okay. So for signal names, you cannot specify the mod port. Last class we have seen. So directly you will write it as arbitif.grant only. Okay. Whenever you are using clocking block, that clocking block has to be specified arbitif.clockingBlock.grant or .request. Whenever you are using the signals within the clocking block, you must specify interface name and which clocking block you are going to use, and in that one what signal you are referring. Okay. And mod ports is not used with signals. Mod port is always used for module names or interface name. Okay, that we have seen in the last class. Next, why can't we use clocking blocks for DUT mod port? And we know clocking blocks are not supported by the design synthesis tools. So for DUT we cannot use the mod ports. So the default behavior of clocking block of sampling the inputs with one step delay and driving the outputs with 0 delay can be overwritten. With the help of default statement. So the default input and output queues are specified this way. Input 15 nanoseconds queue, output 10 nanoseconds queue. The meaning is inputs are sampled 15 nanoseconds before the positive clock edge and outputs are driven 10 nanoseconds after positive edge. Writing the default input and output queues indicates inputs are sampled 15 nanoseconds before the positive clock edge and outputs are driven 10 nanoseconds after the positive clock edge. So this is how you can specify clock queues required. You can override the default clock queues using default statements. Already we have discussed there will be a race condition exists between test bench and design if both are simultaneously driven by the same clock. That means when DUT and test bench are going to be modeled using modules, and all the modules are going to be executed concurrently in the program, okay, in the simulation. So By that time there will be existing a race condition. So we will see one example for the race condition. Okay, so look at this example. So here we have discussed, you have defined a memory module, okay, where the inputs for the memory modules are going to be start and write signals, okay, and address and data is also given. Address is input signal and data can be input output, as we know, okay. And internally we have discussed the we have declared a memory two-dimensional array of 250 locations. Each location can store 8 bits of data, okay. Then how it is executing, always at positive start. Whenever a positive edge, that means whenever start signal changing from 0 to 1, then by that time if write is equal to 1, the data is going to be written into the specified memory location. The data is written into specified memory location when a start signal is changing from 0 to 1, by that time if write signal is equal to 1. Okay, so we are going to checking this functionality by writing a test bench. Okay, so for test bench, okay, inputs of DUT will be outputs for the test bench. So write and start are going to be output signals, okay. Address and data is also output signals for the module, okay. So now this is how we have written. First start is equal to 0, write is equal to 0, wait for 10 nanoseconds, next give the address value, data value, next start is equal to 1, write is equal to 1, end module. We expect that one, okay. The output what we expect is start is equal to 1, previously start is equal to 0, now we made start is equal to 1, and we have also declared write is equal to 1. So we expect the data of 5A is going to be loaded into a specified location of 42. This is the memory location where the data stored is 5A is going to be happen, what we expect. But this is not happening due to the race condition. What is the race condition? Now we will see. Okay, so look at this one. Initial block. If you are looking at initial block, initial and always blocks are procedural blocks and the statements within that are executed sequentially. So first step is start is equal to 0. As soon as start signal is going to be given, okay, the program is going to be starts executing. So as soon as start is equal to 0 and it executes, since there is no positive edge, it doesn't do anything. Next write is equal to 0 and afterwards write value is going to be given and waited for 10 nanoseconds, address is given, data is given. So address and data has some new values. Address and data has new values, and again what we have given is start is equal to 1. As soon as start is equal to 1, okay, as soon as the start, because you are going to give test bench and it is your DUT. So as soon as you are going to give start signal, this program starts executing. So always at the rate pause edge clock. So a pause edge clock has occurred because previously start was 0, now you are making it as 1. So a positive edge is coming. As soon as positive edge is coming, what is the right value? Right value is at previous place. That means right is equal to at 0. So no data is going to be loaded into memory. No new data is loaded into memory because write signal is still at 0. After this positive edge, you explicitly made write is equal to 1. But whenever write is equal to 1, there will be no edge. So this signal doesn't have any effect on the program. So how can you make this one as effective? You can make effective as start is equal to 1 writing. After write is equal to 1, if you write start signal, then that will be having effect. So that means the start signal is going to be coming early than write signal. So this is called as race condition. Due to this one, the expected outputs won't come. the expected outputs won't come, because we expect that initial block is a sequential block, and all the statements are going to be executed within no time. That means practically in delta time. Okay, so at the end, okay, whatever the final values, according to that one, the DUT has to execute. But this is not happens when both test bench as well as memory are written in terms of modules, because modules are at the same hierarchy. When you start simulating, okay, both are going to be executed concurrently, so there will be a race condition exists which starts early, that will be picked up. So how to get rid about of this problem? For that purpose, if we have a situation, let us assume, you can think, okay, assume that one, there is a chance that you can make test bench separate from module, so that module will be at one level of hierarchy and test bench will be at some other level of hierarchy. So based on that one, okay, you are not saying this is also a module. Okay, if you are going to be differentiating from test bench, if you are differentiating test bench from module, then definitely you can say both are not going to be executing simultaneously. So we expect that first DUT will be executed and proper values are going to be after that the test bench are going to be giving the values to the DUT, and the cycle is going to be repeats. Okay, so to make test bench and DUT are not at the same level, to distinguish both things, SystemVerilog introduces a separate block called as program block, where this holds the test bench code. So program block, wherever you are seeing a block of code starting with program keyword, which says that is the test bench for the module. So both are in the same program. Module is DUT, whereas wherever your program is there, that holds the test bench related to that module. So test bench code will be in a program block, so that you can differentiate both. What are the characteristics of program block? Program block, okay, a program block can contain code and variables, but it cannot be instantiated other modules. So simply what program block can have is, program block can have variables, okay, input output variables, and some code. That means initial block, always block, within that one you can write some code. Okay, but it cannot have instantiations of any module. Instantiation is not allowed, any interface instantiations, any other program block. That means another test bench code is also not possible to be inserted into this program block. What you can simply have is, you can have the input and output variables, and you can have the some code, okay, functional code and variables. Now we see different timing regions, okay, in Verilog as well as SystemVerilog. So first we start with Verilog. Okay, in Verilog we know that one, design and test bench both are going to be written in terms of module, so they are at the same level. When they are at the same level, okay, if you are observing this diagram, assume that one, these are the 4 blocks. Okay, when both are at the same level, only 2 blocks are going to be present, and these third and fourth will not be present. Only these 2 blocks are going to be present. So since both are written at module level, and within a module, if you are going to be checking, the statements can be divided into, okay, some blocking statements. Blocking statement means the statements which uses the symbol. Non-blocking statements, the symbols, the statements which uses the symbol. Statements, non-blocking statements, and zero delay statements, okay, for clocking blocks. while driving the signals. Zero delay statements, hash. Okay, in the test bench, if you wait for something or like this is hash delay statements. Okay, and some assertions are nothing but just verifying the functionality of your DUT. Okay, by writing some assertions. These statements, entirely your modules will consisting of only these statements. Out of them, in each region, okay, in each region, which statement is going to be executed, it is predefined. So this is from previous time slot to next time slot. You will have only two regions, active and observed region. You don't have the reactive and postponed region. Okay, when you are writing both DUT and test bench at the same module level, like in Verilog. So in active region, if you are exactly looking at active region is again divided into three blocks, that is active region, inactive region, NBA region. In active region, blocking assignment statements and display functions are evaluated. That means $display, $monitor, those are going to be executed within the active region. So blocking statements and display functions are executed in the active region, and zero delay statements, okay, zero delay statements are executed in the inactive region. And NBA region, okay, NBA stands for non-blocking assignment statements. Non-blocking assignment statements. The non-blocking assignment statements are going to be executed in the NBA region. So these three are going to be treated as a one single active block. And after this, you will have observed block. In observed block, assertions are going to be evaluated. In observed block, assertions are generally written in concurrent nature. So all concurrent assertion statements are executed, sample during this region. Okay, and after this they will be given to postpone region. So that means they will be going to the next level. So this is how the statements present in test bench as well as module. So both will be having the same statements, blocking statements, okay, test bench as well as DUT. Both will have blocking statements, non-blocking statements, delay statements, display functions, concurrent assertions, non-blocking assignments. Okay, all are going to be simultaneously executed from test bench as well as from DUT. Okay, so there will be race condition is existing. For that purpose, SystemVerilog is including the program block. So in SystemVerilog, test bench code is in program block. So design module and test bench module are both not at the same level. So due to this one, SystemVerilog understands that first the DUT program, the DUT statements related to the DUT block, that means module block, are executed in the active and observed regions. Okay, then the program block, the statements in program block, again in program block you will have the same type of statements. Okay, blocking assignment statements, non-blocking assignment statements, display statements, okay, assertions, all are going to be there, and those will be executed in reactive and postponed region. Okay, so if you are looking at reactive, okay, so the program block code executes in the reactive region, which starts after the observed region. After the observed region, even after observed region also, okay, if anything is going back, that means previously after making start signal is equal to 1, by that time write is equal to 0, but after this write is equal to becoming 1, so that is also given back to your DUT and it executes, and finally a positive edge with write is equal to 1 is going to be taken effective, and that will be applied to this reactive region. So you will get proper outputs. You will get proper output. All those things, that means even if anything has to be changes to be made in the same clock cycle, that will be made using this feedback. That will be done with the help of feedback within one clock cycle. Within one clock cycle means it starts from previous time slot to next time slot. The time between previous time slot to next time slot is one cycle. Okay. So in reactive region, blocking statements and display functions of program block are executed. In inactive region, delay statements of program block executed, and in NBA region, non-blocking assignment statements, okay, of program block are executed. And finally postpone region, okay, after all, even in the test bench also, if you are doing something, that will be, if it is again invoking the DUT within the same clock cycle, that is also possible with the help of this feedback. Okay. And finally the final values are going to be sampled in the postpone region. So in postpone region, that is last region of SystemVerilog, monitor strobe statements are executed. That means all the executions are completed. Your final results are going to be awaiting, and that can be displayed properly. So in postpone region, you will have monitor and strobe statements to display the execution, the stabilized execution, the final execution after all feedbacks have been completed. So we can say now the module is going to be executing in active and observed region, and program block is executing between reactive region and postpone region in the reactive region, and final values are going to be sampled in postpone region. Due to that one, we can confirmly say there will be no racing occurs between DUT and test bench. We can confirmly say that one, there will be no racing occurs between DUT and test bench in case of Verilog. So the advantage is this, okay, the time doesn't always go forward like this. Okay, there is always a situation that events observed in observed region and reactive region can trigger further, okay, back into design events, okay, in the active region in the same current cycle. This is the advantage you will get. Okay, due to that one, the final code is going to be the proper one what we expect. Okay, and after all these things has been completed, last in the postpone region with sample signals at the end of time slot. Okay, so after entire design activity has been completed due to feedback also, and finally you are going to sample the values in the postpone region. Okay, so this is summary of regions. Active region, simulation of design code. Observed region, evaluation of SystemVerilog assertions, already we have seen. Reactive region, execution of test bench code in program blocks. Postpone region, sampling of design signals for test bench inputs. Okay, so due to this one, we can confirmly say test bench and modules cannot have a racing problem. Okay. And already we know that one, whenever we are declaring a clocking block, the default timing is, okay, the default timing to sample inputs with a skew of one step. Always you should take sampling inputs for the test bench. That means you are sampling the outputs of DUT which becomes input for the test bench. So sampling should be taken with a skew of one step. Already we discussed this. But this one step indicates, okay, this one step, if the clock edge is going to be occurring at this point, the one step is after this entire region. So that one step indicate you are sampling in the postpone region. Okay, by that time we have not discussed, okay, that one step means within the current cycle you are dealing with postpone region. And drive the outputs of test bench to the inputs of DUT with zero delay. This is default timing characteristics of clocking block. Okay. So this one step, you can think it as the one step is how much time it is. The one step means it has to wait for some time. The outputs of DUT is going to be sampled after some time. That after some time, okay, whenever there is sampling after one step, you can think just you are going to add a D flip-flop between, okay, the output to be sampled and the actual output of module. So you can think in this way, but it is not exact. To remember it, you can think in this way. Okay, just remember by imagining in this way. It is not the correct way. Okay, but always it takes some amount of time to specify that one in your mind. You can make an imagine in this way. So in this we are going to check with examples the different timing regions. Are they taking some amount of time while sampling, and while driving the signals it should be with zero delay. Is it happening or not? That we will go with some example. So look at this one. First we are going to sample the signal. Okay, so why we are writing interface signal sample? Always the test bench and design under test DUT are communicated through an interface. So here now we are going to have the discussion is a signal from the output of DUT to be sampled at the input of test bench. That means program block. Okay, and we know that one whenever you are using program block, okay, first the statements in design DUT is going to be executed, and after that one active region and observed region, then the statements in the program blocks are going to be executed in reactive region. So definitely, even if you are going to give some values for the signal, that means the signal between DUT and TB, okay, output of DUTs are given some values that will not appear at the test bench input at that instant. It will take some amount of time, that we are calling it as hash one step. That hash one step is going to be the maximum of one clock cycle. It can be of at most one cycle duration. So look at this one. Now the arbiter is going to be arbiter example as DUT. Here the output of DUT is grant signal. So it has to grant the signal. Assume that when the grant is going to be giving, okay, after 70 nanoseconds the grant value is 1. After 170 nanoseconds grant is 2. After 250 nanoseconds grant is 3. Okay, here this is somewhat different, where we are going with fork join statement. Okay, we will discuss it later. Fork join statement, the statements within fork join are executed parallelly. Statements within fork join are executed parallelly. That means you are only dealing with grant signal of DUT, but that will be given value of 1 at 70 nanoseconds, and the value is going to be overwritten at 170 nanoseconds by 2, and again the same signal value is overwritten at 250 nanoseconds by 3. So you are dealing with the one signal only, but you are changing this value at different times using this fork join. Since the statements within fork and join are executed parallelly, so this is a signal of interest DUT arbit.grant. Okay, so this is 50 nanoseconds, so make it as this is 70, and this is 150, and it will become 170, this point, and next 250 is nothing but exactly this point, that means clock edge. So we have applied a grant signal with different values at different times. If you are connected with program block to test this one, how the program block is going to be taking this grand signal as input. Now the program block has to sample these outputs, and sampling of these outputs are always done at postpone region. Postpone region after #1 step. So even if the DUT signal is changing at 70 nanoseconds, even if the signal is changing at 70 nanoseconds, but test bench is going to be having effect from next clock cycle. Okay, this is next positive edge. So this is the we can say the difference is going to be the difference from the preponed edge to postponed edge, preponed region to postponed region. And again at 170 nanoseconds the grand signal is going to be changed, but it is going to be having effect at 250 nanoseconds. Why at exactly its clock edge it is changing? Because grand signal is going to be synchronizing signal which has been defined in the clocking block. Okay, and even if the, look at this one, even if the grand signal is changed at positive edge itself, it doesn't have effect at the test bench input, because it will take some amount of time, because after execution of DUT and feedback, okay, then test bench, and finally you are going to get the value in the postpone region. That makes at most of 1 clock cycle. So even if you are changing the value at positive edge, okay, and this value will be effective in the test bench after 1 clock cycle. So this says the importance of #1 step. So always the test bench inputs will have some delay between the DUT outputs by default. Okay, by default it is #1 step. Otherwise you can also specify the amount of time using default statement in the clocking block. Because in SystemVerilog always test bench and DUT are communicated through interface clocking blocks only. Okay, so this is what we verified. Always sampling is going to be done after #1 step. Next we will see how to drive the input signals. How to drive the input signals of DUT from the test bench through interface only. Again, driving interface signals through a clocking block. Okay, because DUT and test bench are always communicated through clocking block. Okay. So this point already we discussed. While using the clocking blocks, if you want to refer any signal, okay, then you must use the notation of interface dot clocking block dot that particular signal. This is the correct notation to be used. This is legal, and if you are not using clocking block, it will be saying the error, because whenever you are using clocking blocks in the interface, always you must follow this type of notation for the signals. Okay. So now we are going to drive the interface signals through a clocking block. Now we are driving the interface signals, driving the signals from test bench inputs to DUT outputs. So here the situation is, now you have a now you have a test bench and you are driving the DUT. And when you are driving DUT through clocking block, how the driving signals are going to be applied? Okay, through clocking block only. So we know that one already, the characteristics of clocking block. By default, if you are driving signals, then it takes #0 delay. #0 delay. While sampling it takes #1 delay, that we have seen in the last slide. Now #0 delay, the meaning is, if you are going to apply, okay, if you are applying an output of test bench, if the output of test bench is changes at this active edge, that applied immediately to the DUT, that applied at that instant itself to the DUT with no delay. 0 delay is nothing but at exactly, if you apply if you apply the output of test bench changes, the changes in the output of test bench at this edge is applied directly to the DUT on that edge itself. Okay, if you are making after this edge, that will not appear in the DUT. If you make any changes before this one, that appear at this edge. If you are making any changes in the test bench outputs before this clock edge, those will be appear at this clock edge. And even if you change at this clock edge also, that will appear because of this zero delay. But after changes of this clock edge will not appear, that will appear in the next clock edge. Okay, so to verify this one, what you should do is you must apply the changes, that means output of test bench should be changes, and that you have to monitor in the DUT. Okay, now the outputs of test bench are going to be given different values and they will be monitored at the DUT. So whether the hash 0 is going to be taken by the system by default or not. Okay, for that purpose, right, this is the test bench because it starts from the program keyword and the name of the test bench. Okay, input for this test bench is or if is the input, which is of interface type, and that interface is using a mode port called test. Okay, and again we are going for the fork chain statements. Fork chain statements already we discussed. The statements within fork chain are going to be executed parallelly. Okay, so at 70 we are going with now request signal, because request is the output of test bench and input for the DUT. So request is going to be given at 70 nanoseconds with value 3. Okay, so at 70 request value is given as 3. Okay, next the request value is changed at 170 with 2. Next request value is again changed at 250. Okay, now with one value. Now observe, first value request is going to be changing at 70. Okay, this is not at clock edge, so after the clock edge the value is changing, so it won't appear at the DUT, so this will be appearing at next clock edge. Okay, so on the next clock edge this is appearing, and next at this edge is anything changes? Nothing. So again the signal is going to be changing at 170, and at 172 is going to be changing. It should appear at the next clock edge, but okay, at next clock edge what you are giving is the request signal is going to be changes to 1. So this 1 is effective at the next clock edge. At 250 you are changing request to 1, so this 2 will not appear because it has zero delay. Due to that zero delay, okay, the signal 1, which is output of test bench, that changes at this exactly at this test bench, that will be given to DUT with no delay. So requesting or driving the interface signals to the DUT makes zero delay by default. So this 2 is not going to be appear at the output. So which signifies that the driving of interface signals or driving of outputs of test bench to the inputs for the DUT will go with hash 0 delay. That can be signified with this example. Okay, so these are the two important characteristics of DUT. These are the two important characteristics of clocking block. Okay, clocking block inputs, test bench inputs are same. Clocking block outputs, test bench outputs are same. So if you are driving the signals from clocking block, then it takes hash 0 delay. If you are sampling the inputs for the test bench, that means inputs of clocking block, if sampled, they will take hash 1 step delay. So the disadvantage is when you want to try to drive signal request of 2 value to the DUT, it is not happening because you are specifying the signal values with respect to time, and we don't know at what time the clock edge is going to be appearing properly while writing the test bench. So instead of it, you can write the same thing with respect to clock edge. with respect to clock edge, that means with respect to number of clock cycles. So you can specify this way. Okay, hash hash followed by 2. So hash hash followed by 2 means once you are giving this request equal to 0, this must be applied after 2 cycles. So wait for 2 cycles, then assign. You are giving this signal. If you are not writing hash 2, then it will be assigned at that instant itself. Okay, at that clock edge. But if you are writing in this way, so from this point onwards, whatever the time you are giving, whatever the at what time this signal is going to be written, that will be assigned after 2 clock cycles, after 2 positive edges, if your clocking block is positive edge sensitive. Okay, so this way if you specify, then there is no loss of information like in the previous case. How the signal with request with 2 has been not applied to the DUT. Okay, so you can specify this way, but this is illegal specification. Why illegal specification? Your system may be having so many number of clocks. Okay, so by that time, if you are writing hash 3, which clock you are referring, system cannot understand whether you are referring clock 1 or clock 2 or clock 3. So you must specify the signal with proper clock. That means the proper clocking block. So if you are writing in this way, arbitif.cb, so you are referring particular clocking block. So that particular clocking block is referred to a particular clock signal. So after 2 clock cycles of that particular clock, this signal will be allowed. This signal will be assigned. So if you are simply writing it, it is illegal. Okay, and even instead of it, you can also you can also write hash 1, hash 0. Okay, hash 0 is nothing but with no delay. Hash 1, hash 1 means after 1 clock cycle. So even if you are making the change at exactly positive edge, by that time also the assignment will take place after 1 clock cycle. Okay, even the output of test benches changes exactly at the clock edge. By that time also hash 1 means it takes 1 clock cycle delay, and on next clock edge only the signal will be applied to the DUT. But whenever you are writing hash 0, that makes within no time. Okay, within no time it will be applied, drives the value immediately. If the clock is asserted, that means if a signal is asserted on the positive edge, okay, and you are specifying hash 0, so it will be within no delay, it will be applied to DUT. Okay, this is how you have to specify. You can specify. Okay, previous way of specifying is called as asynchronous way, whereas this is called as proper way. You can also specify with respect to clock edges also. So one important thing you must observe is while giving the while driving the signals, you must use the non-blocking assignment type. While sampling the signals, you must use blocking assignment statements. Remember it. Okay, while driving the interface signals to the DUT, you must use non-blocking type statements, and while sampling the interface signals, you must use blocking assignment statements. Remember this important point. Next, okay, so in a clocking block we have seen either input signals or output signals. The communication between test bench and DUT is always through interface, and in the interface always if you are using signal synchronous signals, you must specify with clocking block. Okay, so whenever you are using clocking block, you are specifying the directions of the inputs also, and using mod ports. And by that time, if there is a signal called as in out, okay, bidirectional signals, then Okay, the bidirectional signals always specified with wire outputs, wire type. The bidirectional signal should be always used of type wire. This is very important. Okay, if it is in type or out type, directly you can go for the logic. But if it is okay bidirectional type, always use wire type and everything is going to be same. Since it is wire type, it can handle the values. It can has the Z also, it can also valid. So this is how you can assign those signals. Data signal can be given Z, data signal can be something given, value can be given. Okay, so this is a data is a bidirectional signal, so you can give the values as well as you can retrieve the values. Okay, both bidirectional, you can give the values as well as you can retrieve the values. So if you are observing this one, the first statement is you are sending value to the data. So tri-state bus, you are saying data is a tri-state bus and you are giving Z is going to be given to the data. Okay, and you are waiting for 1 clock cycle because MIF dot CB dot data. So the data present in this is waiting, you are waiting for 1 clock cycle and afterwards you are displaying it. Okay, and there is a small mistake in this one, it should not this is MIF. Okay, the output block. MIF is the input for the program block. So for that purpose you are giving data and you are displaying the data, waiting for the data, displaying data. Once you are given the data and afterwards you are displaying it. So this is application of how you are going to use the bidirectional signals. The only thing is, if you want to use the bidirectional signal, always make it as wire type. That's only the important thing. So till now we have seen program blocks in examples. Always you have used initial blocks only. We have not used always block. Why are always blocks not allowed in program blocks? That means while writing the test bench, we don't use the always blocks, we use only initial blocks. Okay, because always blocks, always as the name indicates, okay, as soon as a signal triggers, if an event occurred on the positive edge or negative edge, okay, by that time the statements within that always block are going to be executed and it keeps on running. But with respect to test bench, what is our aim? You must apply a set of test inputs and you are going to check the response and you are stopping that one. Okay, so initial statement is better suited compared to always block. Okay, so always if you use, it is never ending process. Okay, so instead of that one, better to use initial, because initial itself is going to be stops after the last statement in the initial block. Okay, so if you want to come out of that program block, then by using always block, if you want to come out of that program, you must explicitly call the exit statement. Okay, so where to put this exit statement is going to be again a problem. Okay, by that time whether it is able to complete the task of verifying or not, okay, you cannot say that one. So instead of using always block, you can use initial block in the program. That means test bench. Okay, if still you want to use some always block you want to use, okay, so by that time instead of always block you can use initial with forever. Like generally while generating a clock signal, you can use either always block or initial with forever also you can use to generate a clock signal. So this type also you can use if it requires, but it never requires for a test bench. Okay, next, normally you have seen how to generate a clock signal. Okay, so the general way is nothing but simply you are going with always. Okay, after #5 clock equal to not clock. So you are generating a clock signal of time period 10 in this way. So generally whenever you are writing these statements, that means generation of clock, will it be kept in test bench or will it be kept in module? Is it better to have clock generator in DUT or program log? Okay, it is always better to place in the DUT. It's not that much suitable when you place it in the program block. The program block is not the place to put a clock generator. Okay, when you are placing it clock generator, there will be some race problem exist, because if you are placing the clock signal in the program log, that means test bench clock, this clock signal is going to be executed at the reactive region. Okay, whereas the design part, the DUT statements are going to be executed, okay, in active region, but by that time you are specifying upon paused edge. In module writing, in DUT you are writing at the rate of paused edge clock. But have you clock is generated, the clock is generated in the reactive region, but you are defining these things in the DUT. So it is not possible, it is better place to generate the clock in the DUT itself. If you are generating DUT itself, it is better to execute the statements like this in DUT. Otherwise the program try to execute these statements by the time clock is undefined. Okay. So even if you can write the statements like this, okay, but these are not proper way. Okay, always use the clock generator statements in the DUT itself. Okay, so the clock generator should be instantiated at the same level as DUT, so that it can drive both DUT and test bench, and there will be no race conditions. Okay, avoid race conditions by always putting the clock generator in the module. Module means DUT. Okay, and all clock edges are generated with a blocking assignment statements, so that they are always executed in the starting region of active region. Okay, so you might have seen always you will use a blocking assignment statement only for clock generation, so that okay, within the active region itself you have seen first one is active, next one is inactive, next one is NBA region. So the clock generator should be generated at first level, so you must specify with blocking assignment statements. Okay, and one more good thing to generate the clock is you have to generate a clock with a local signal. Instead of going with the actual clock signal, you make it as local signal. So look at this one. Okay, the better way of generating the clock generator in a module. So clock generator has taken the input signal as clock. Okay, and you have defined one local input signal as local clock equal to 0, and you are assigning clock equal to local clock. Okay, and this local clock is going to be applied to clock, but local clock is going to be changes at every 50 nanoseconds. So the time period of 100 nanoseconds is going to be the clock, and that will be applied to clock. Okay, instead of writing #50 clock equal to not clock, you are going to generate clock with local clock that will be assigned to clock. Whenever a test bench runs, how the system knows that is the end of simulation. When the simulation will be ended, how the system knows when to end the simulation. In case of Verilog, okay, there are two ways to end the simulation. First one is nothing but system will execute all the statements in the program block. Okay, that means all the statements in the initial block will be executed, and after executing the last statement it will terminate. Otherwise you can also terminate in the middle, by using a $finish keyword. So these are the two ways in Verilog it happens. And if you are coming for the SystemVerilog, in SystemVerilog we are writing test bench in a separate block. That block is called as program block, and you cannot have any instantiation of modules or interfaces or any other program also, but you can have any number of simultaneous program blocks. Remember it, you can have any number of simultaneous program blocks, okay, but you cannot have any instantiations of program blocks within it. You cannot have any instantiations of modules or interfaces. So let us assume your program has only one program block. Then it simply performs in the similar way as Verilog. That means executes all the statements in the initial block, and after executing the final statement in the initial block, then simulation turned off. Okay. If let us assume if your program, if your design has more number of program blocks, then the system stops simulation, okay, after executing all the statements in all program blocks. That means the last statement in the last statement of initial block, okay, when it completed, then it stops. By the time all other program blocks have been executed, okay, which takes longer time. It will be given that much time, and in that program block also the last statement is executed, then it stops. Otherwise you can also specify in any program block, if you are specifying $finish, that also stops execution of all program blocks, okay, it stops simulation. Otherwise, if you want to skip any one program block, SystemVerilog adds a new keyword, adds a flexibility of turning off a particular program block and you are continuing other program blocks. For that purpose, this is $exit has been used. $exit is the keyword which is mainly used to come out of a particular program block. Okay, you can terminate a particular program block, okay, early by writing this $exit, and then other program blocks are continuously running in simulation. Okay, if you want to come out of all program blocks, you can use $finish. If you want to use if you want to come out of only one particular program block, then you can use $exit. This is one extra keyword you can use in SystemVerilog. So you know that one, the simulation ends whenever the last statement in the initial block has been executed. So can we say that one, by the end of that statement, okay, all results are going to be finalized, okay, then you can monitor the results, or you can display those results. After that you can declare as you can monitor those results. For that purpose you can use a final block. Okay, so Verilog or SystemVerilog are having, instead along with initial and always block, it also has final block. As the name indicates, a final block is going to display the end results, okay, that contains the code to be run just before the simulation terminates. So this is the last statement. After execution, it continues and it displays the final conclusion of your test bench. Test completed with how many number of errors, how many number of warnings, and what is the final value. You can also write some